We have in fact already seen an application of the idea of the unit tangent and unit normal vectors, because in previous excuse me, in previous clips we did calculate the unit tangent and unit normal vectors for this vector function. Remember, this vector function gave us an ellipse, semi-major axis 3 in the x direction, semi-minor axis 5 in the y direction. And we calculated the dr dt vector we calculated the unit tangent vector. If we use the time interpretation, this dr dt vector is a velocity vector, so our unit tangent is thought of as velocity over the magnitude of the velocity, giving us the direction. The dr dt over magnitude dr dt notation also gives us our unit tangent vector. We calculated the derivative of the unit tangent vector, and then we used that derivative to calculate our unit normal vector. Now, I'm not going to repeat the details of that calculation, and you'll probably find that a relief, but you can go back a couple of clips if necessary and see that discussion. The ultimate idea here is that at any point of this ellipse, we have a unit tangent vector, a unit normal vector, our acceleration vector, which is our r double prime, and that acceleration vector has components in the normal and the tangent directions, which are easily calculated. The tangential component of our velocity is of our acceleration is found simply by taking the dot product of r double prime with t, the normal component by taking the dot product of r double prime with n. In other words, we're just projecting the acceleration vector onto the unit tangent vector and onto the unit normal vector, and the projection takes very simple form when you're projecting onto a unit vector, simple dot product. Here we have a picture very similar to the pictures we've seen in the preceding. Here's a curve where the inward unit normal is away from the r of t vector, unit tangent vector, r double prime interpreted as an acceleration vector, and down here we have the same vectors, and we can project the acceleration vector onto the tangent vector, unit tangent vector, and onto the unit normal vector, obtaining our vectors A perpendicular to the curve, A parallel to the curve. And as another example, let's consider now the function r of t equals -3 sine 9ti plus 7 cosine of 9tj. Now this is so far just another ellipse, but we're going to then add a k component. We'll have a t squared k. Now our ellipse in the I and j direction is going to have a semi-major axis of 3, or semi-minor axis of 3. That'll be in the x direction, a semi-major axis of 7 in the y direction, and we sketch the ellipse and should know how to do that by now. When we go into 3 dimensions, when we try to do our 3-dimensional vector, our x and y components are always going to follow this ellipse. But because of the k component, that ellipse is not always going to be down in the xy plane. In fact, the only time that ellipse occurs in the xy plane is at t equals 0. So what I've done is I've sketched a x, y, z set of coordinate axes. I haven't labeled the z, but you know which one that is. The labeling is going to get in the way of what I'm going to draw. At t equals 0, we're actually on the ellipse in this plane. Now, of course, at t equals 0, the I component is 0 and the j component is 1, which means that we're at at t equals 0, we're in the xy plane at the point 0, 1, 0. And that would be the point up here, and it's not 1, it's 7, because, well, obvious why. Okay, so we're at this point at the t equals 0. Now, a later plane, okay, a little bit later, we're now in a plane that lies above the xy plane. So I've tried to depict in a different color the square, or the rectangle, in which we would construct the ellipse on which our point is going to lie when t equals some later unspecified time. We're not going to worry about that just yet. We'll figure that out in a minute. Figure out what kind of time scale we want to use. At a later time, well, what's happening to the k component? We have t squared k. That means that our k component is going to start small, and it's going to change slowly, but it's going to change more and more quickly because t squared behaves in that manner. So at this later time, we're going to be in a plane that's higher than the second plane by more than the second plane is in the first. In other words, the spacing between the t equals 0 and a slightly later time. If we sketch this at an equal time interval after we're at this position, we will be able to do that by sketching a y-axis here, an x-axis here. Now, when I sketch this x and y-axis, I'll call that x prime and y prime. Prime not indicating a derivative, but just a different auxiliary set of xy axes. When I construct those, I make sure they cross at the appropriate point of the z-axis, and that the y prime axis is parallel to the y-axis, the x prime axis parallel to the x-axis. I then construct the same ellipse in this plane. Okay, we come out a distance of representing 3 units, a distance equal to the distance between the origin and this point down here. So we're going to have this point, an equal distance in the y direction, which is going to put us right here, and in the negative y and the negative x directions. And those points lie directly above and below these 4 points. Then we sketch our rectangle, keeping the sides parallel to the x and y axes. Can't sketch the whole thing because we're interfering with our labeling here. And it's not a perfect sketch, but we can see that this rectangle lies above the preceding 2 rectangles. And we're going to use, we're going to sketch in the ellipses, and we're then going to use those ellipses to construct 3 points on this curve, and think about the motion in 3 dimensions that would correspond to this curve.